Hi everyone. In this video, we're going to be looking at predictions, particularly how we predict the y variable in the regression. So suppose we estimate a particular regression equation and y hat is given by beta naught hat plus beta 1 hat times x1 and so on up to xk. Now, if we are interested in finding out what's the average value of y for a certain specific values for the different x's. So suppose say x1 is equal to c1, suppose x2 is equal to c2, xk is equal to some number ck, and so on. At those particular x values, what is the predicted value of y? And how do we obtain that? We just plug in these values of x1, x2, and so on, and we plug that into our predicted regression equation. And the answer that we get is called y hat for those specific x values. And that's called so we say that for observations that have their regressors taking on these specific values, the average value of y is predicted in the regression is given by y hat. So if you have a regression of, say, college GPA on high school GPA and attendance rate, and if you plug in, say, high school GPA is 3.5 and attendance rate is 90%. So for students who have attendance 3.5 and, GPA, high school GPA 3.5 and attendance rate is 90%, on an average, we would predict that their college GPA is something so and so. So that's the idea. So, and let's go ahead and call that prediction. We're going to call that theta naught. Okay. So how do we obtain theta naught? By just plugging in the different values for the x's. Now, if I were to think about this relationship in the population, I'm just looking at the expected value of y given the x is fixed at c1, c2, and so on up to ck. That's my theta naught. Notice how the theta naught equation just has no hats in it, right? You just have the population parameters. So how do we estimate this using the sample? Well, we put hats on top of everything now, right? We have beta naught hat, beta 1 hat times c1, beta 2 hat times c2, and so on up to ck. So this is the prediction that we can get from our sample. Now, why am I talking about all of this? Because we're going to figure out, we're going to go one step further now. Now, in a particular sample for that particular regression line, I can figure out theta naught hat. Now, we know that when you take different samples from the population and estimate the same relationship, you're going to get different regression lines. Of course, in theory, in practice, we don't do that, but this is a theoretical thought experiment to motivate what we're going to do next. Different samples give us different regression lines. And with different regression lines, I'm going to get different theta naught hats. So if, as a reader of this result, of this equation, if I want to know with what degree of certainty can I expect my theta naught hat to take on a certain value, meaning for some values c1, c2, and ck, I can predict a theta naught hat. But is there a range of values that I would expect my theta naught hat to take on in different samples? In other words, I'm going to construct a band of values around that theta naught hat to tell me, say, whether in 100 samples, 100 different samples, can I be confident that 95 of them will, in 95 of those intervals, my theta naught hat will just fall within that interval. So it's just that band which tells me that if I just take repeated samples, I would expect that predicted value to fall in that band. Or in other words, I think I'm going around a little bit. Let me, hopefully this time I'll nail it. So my goal is to find theta naught, but I only have access to theta naught hat, which can vary across samples. So I want to now construct a band of values such that in 95 out of 100 cases, my true theta naught will fall within that band. So I'm going to construct a confidence interval for theta naught. How do we go about doing that? Let's see. Well, to construct a confidence interval for anything, we need the estimated value and its standard error. Well, how do we get a standard error for theta naught from linear regression? We're going to use the trick that we learned in chapter 4, where when we wanted to test a hypothesis of linear combinations of parameters, we transformed the linear regression. And we're going to do something similar now. Well, we know that theta naught is just beta naught plus beta 1 C1 plus beta 2 C2 and so on up to beta k ck. If I rearrange these variables, these expressions, I get this. Now I'm going to go ahead and plug this into my original regression model. And when I do that, what happens to my original regression model? In place of beta naught, I substitute this expression. And you see how there's a minus beta 1 C1 and then there's a plus beta 1 X1 here. Minus beta 2 C2 plus beta 2 C2 and so on. So y can now be rewritten like this. Work through the algebra and you'll see how that works. So what we've now done is transformed our regression model in such a way that the intercept measures the prediction that we care about, and all of the regressors have now been transformed where you take a regressor and you subtract the particular value of that regressor that you care about. So we are setting x1 at c1, x2 at c2 and so on, right? So you're going to take every regressor and subtract that relevant c value from that regressor, construct a new set of regressors and then run this regression. When you do this, your intercept will give you theta naught hat, and you will automatically get the standard error of theta naught hat as the standard error of the intercept. And once you have those two, you can construct a confidence interval for the theta naught hat. What is theta naught hat again? The predicted value of y when you fix your x variables at c1, c2 up to c2. And we're doing this confidence interval for theta naught because different samples will show up different values of theta naught hat. So can you construct a band such that in 95 or 99 out of 100 cases, the true theta naught will be contained in that band? So let's see. So here's an example where college GPA is a function of SAT score and a few other variables. Now, we're interested in predicting college GPA when SAT score is say 1200, another regressor is set at 30, and another one is set at 5. So if you plug in all of these values into this equation, right? So if you do 1.493 plus 0.00149 times 1200 minus 0.01386 times 30 minus 0.06088 times 5 plus 0.00546 times 5 squared, the answer turns out to be 2.7. So for these values of the regressors, the predicted college GPA on an average is 2.7. But we don't know its standard error. So what do? We bring in the changes we described earlier. I'm now going to define new regressors where every regressor is the original regressor minus the particular value that we decided for it. So SAT 0 is now SAT score minus 1200, HSPERC 0 is now HSPERC minus 30 and so on. And when you run that regression, the intercept, remember, the intercept is the effect of interest that you're looking for. So, and notice how the intercept gives us the value that we predicted earlier, and we automatically have its standard error as well. And now we have all that we need to go ahead and construct an interval for this prediction. So we're just going to use our usual confidence interval processes to do this. So when you have a large enough sample, we're just going to use normal distribution cutoff values as the critical values. So it's just going to be theta hat plus or minus a margin. that margin is your 1.96 times standard error of beta naught hat. Very similar to how we did it for the beta hats earlier. And so 1.96 is when you're looking at a 95% confidence interval. You could choose, the higher your confidence level, the greater your critical value. So we can go ahead and do that. So 95% confidence interval in this case is therefore given by this expression. So for an average student with the specified characteristics of SAT score of 1200 and other variables, the confidence interval for their predicted score is the range that is given here. Now, we're going to extend this one step further. This is the average confidence interval. This is the interval for an average y hat which stays on your regression line. Given different regression lines, you're figuring out the range of values for those y hats in different samples. Now, if I were to pick a particular point in the sample, not something that necessarily lies on the regression line, but rather a particular unit from the population, such as, say, yi here. If I were to predict the actual value of yi, then in that case, I need to know yi hat, and I need to know the error there. So, and if I were, of course, I missed adding one thing here. If I were to choose a certain values for the x's, say C1, C2, and so on. So in this case, suppose I'm fixing my x value at xi. If my x value is fixed at xi, if I'm predicting the average y, I'm looking at yi hat. But if I'm predicting a particular y, I'm looking at this yi, and it's going to have an error term with it. So if I'm thinking of predicting this one, I should be worried about sampling variations not just in this yi term, but also sampling variations in the error term. What do I mean by that? So for the same set of xi's, in one sample, I could be predicting yi as the outcome. In another sample, I may be getting yi dash, in which case my error term is now, I have negative error. There could be a third sample where that yi is somewhere here, in which case that's the error. So the point is, when you're trying to predict a particular unit, for that you need to account for not just the yi hat for that particular set of x values, but also the variation in the error. So that's what we're going to do next. The algebra may be a little scary to look at now, but trust me, if you just patiently work through it one step at a time, you'll get it. I'll do my best in this video, but I may have to skip through some in the interest of time. So we're now going to construct what we call a prediction interval, which is for a specific unit. Now let's say we're fixing all of the x values at this x1 naught, x2 naught, and so on up to xk naught. They are the values of the independent variables that we are choosing. And given those values, we are interested in a particular y value, say y naught. Okay? And naturally, the error term associated with that value is u naught. So we now want, so y naught is that, so let's say this is y naught. Okay? For the particular set of x values that we have identified, we have narrowed down on this one single point, and we want to see what the prediction interval for that is. That's going to happen in two parts. We all know that y is y hat plus u hat. So there's the predicted value which lies on the regression line, and there's the residual. So how are we going to do that? We first predict y value for those x values using the regression line. And then we see what the prediction error is, which is the difference between your y value, actual y value, and the predicted y value. And I'm going to call that E naught hat. Okay? So that is just the actual minus predicted. So the actual value will all have these population parameters. And then there's a u naught there. And the predicted values will all have the hat counterparts. Now, if I go ahead and take an expectation of this prediction error, it's going to work out to be 0. And that's an algebra which is fairly simple enough. Work through it slowly. So the only hint I will give you is that expectation of beta hat j is equal to beta j. And that just comes from OLS, the blue, the assumptions. So, okay, but we don't need to worry too much about that for now. Let's come to this. So the prediction error is just the actual y value minus y naught hat. So if we were to go ahead and, okay, so we're skipping through a few steps in the process here, but that's immaterial for the explanation that follows. So if we were to write, so let me remove this so that it doesn't confuse you at the moment. I'm just getting to the actual results here and not going through the calculations now because I don't want to confuse you further. So if we were to write the variance of the prediction error, that is given by the expression that you see here. Variance of y naught hat plus variance of u naught gives the variance of the error term. Now there's no covariance term here because by definition y naught hat and u naught have to be unrelated. So the variance of the prediction boils down to these two terms. We can find out variance of y naught hat from our regression. But sigma square is a population entity, and so we need to estimate that from a sample counterpart. So just a quick couple of things before we move further. The prediction error now has two sources of error. So one comes from the variation in the y value itself, the predicted y value, and another from the variation in the error. Now, the predicted y value, that variance will actually shrink as the sample size increases. So in larger samples, this will shrink to a smaller number. Now, the error variance need not necessarily shrink to 0 with the larger sample. So what you'll see is that as you have larger and larger samples, the sigma square will dominate your error variance, the prediction error variance. Now let's move to an example and see, okay, let's see how to compute this error variance. So we know that variance of E naught hat is variance of Y naught hat plus sigma square. But we're going to estimate this sigma square using sigma hat square. So let's see. So variance of error hat, the estimated one, apologies, need to erase that. It's just variance of y naught hat plus sigma hat square. So if I take the square root of this, I'm going to get the standard error. Okay. So we go ahead and write down the standard error. So we can now write down the standard error of E naught hat. And just a couple more points very quickly. From the OLS assumptions, the residual U hat or E naught hat in this case is normally distributed. So if we write down the T, when you don't know the error variance and you estimate it follows a T distribution. So we can essentially write down a confidence interval for E naught hat using the T distribution. And because E naught hat is just Y naught minus Y naught hat, you can come up with a prediction interval for Y0 by just plugging this into this equation. That's just a lot of things that I just said. To summarize, once you identify this E naught hat and you write down an expression for its variance, we earlier saw that its expectation was 0, and we have now written an expression for its variance. From MLR assumptions, this error is normally distributed, and therefore we can write its T stat, and that will follow a T distribution. So Right. So we can construct a confidence interval for E naught hat, and using the relationship between E naught hat and Y naught, which we care about, we can now construct a confidence interval or a prediction interval for Y naught. So, and that is given by this expression that you see here. Now remember, we're talking about finding an interval for a very particular Y value. So we have to also account for how the error term is varying there. And this interval, the particular Y value, will actually be wider than the interval that we are coming up with for the average Y value. So, and you can notice that just in the way we construct the confidence interval. This is for a particular Y value, the prediction interval. Whereas what you see here is the confidence interval for the average Y value. So notice that you have standard error of E naught hat there, standard error of just Y naught hat. Standard error of E naught hat is standard error of Y naught hat plus another number. So it's naturally larger, so a wider margin. Now on to the same example as before. So just by rearranging the terms using the linear, the trick that we used when we are testing linear combinations of parameters, right? We do the same thing. You can rewrite your regression equation. Your intercept is now theta naught hat. So, or in this case, Y naught hat. Okay. So you could think of this as theta naught hat or Y naught hat, the average prediction for that particular set of X values. And the standard error there gives you its standard error. And then the standard error of the regression, sigma hat, is given to you. Now, using all of this, for a particular Y0 value, we need, this is the information that we need to compute this particular expression. You plug in the numbers, and voila, you have your prediction interval. And as I said, this is a much larger interval. So that broadly is about prediction, and just a couple of things to wrap up this segment. After the regression model is run, we also often analyze how the residuals look like. So the residuals are just your actual Y values minus your predicted Y values. So you will see researchers just plotting out their residual maps. So a positive residual means, okay, so if you look at the chart that I've drawn on the slide here, so here is a case where your actual Y value lies above the predicted Y value. So you're under predicting in that case. In the second case, your predicted value is greater than the actual value. So in such cases, you're over predicting. So to understand this under prediction and over prediction patterns, and that can be applied to some very specific contextual examples, people go ahead and do the residual analysis. And just how the residuals are distributed also tells us whether homoscedasticity holds or whether normality of error assumption, whether that holds. So those are other useful applications of doing the residual analysis. Now the last part in the prediction segment, what do you do when your Y variable is in log format? Suppose you have a model where dependent variable is log Y, regressed on a set of regressors. And how do we move from log to exponent and back? So log of say Y to the base E, if that is equal to X, then E power X is equal to Y. Okay, so that's the relationship between log and exponential functions. Apply the same logic to this model. You can now write Y as the exponent of that entire expression on the right. And you can break that down and write exponent of just one part containing all the regressors and another part containing the error term. Now, we can go ahead and compute the predicted value of Y given different X values. And the predicted value of Y, which is Y hat, is just going to be exponent of, instead of betas, you put beta hats. Okay, so before that, let me just do E of y given x. So if I want to find the average value of y given certain x values, I'm trying to predict the average y for a certain x value, set of x values. I just take the expectation operator. So the expectation operator will not apply to any of the x variables. It will directly go only to the error term because we're talking about the population here, right? So expectation is the population average. The sample analog is given by y hat. So I have beta naught hats within the brackets. And in place of the expectation of e power u, I just have the sample average of e power u. So this is nothing but sigma e power ui hat divided by n. Whereas this is expectation of e power u. So that's the population one, this is the sample analog. Now, when we're trying to predict y, when it is measured in logs, if we just go ahead and compute this part alone, okay, if we only take exponent of all just the predicted regression line, we're going to run into a problem. Why? Because we're ignoring this term here. And we shouldn't ignore that term because mathematically we can show that that term is actually greater than 1 or equal to 1. If it is greater than 1, and if you actually just take a prediction as exponent of just the regressors, the predicted regression line, and you stop there, you will be underestimating y hat. You have to multiply that by this particular estimate in order to get your true or better predictions of y hat. And this is something to remember when your when your y, the dependent variable, is in log terms. So this sort of prediction is referred to as a smearing estimate in the literature, and it helps us get better in how we predict using regression models. And with that, this chapter comes to a close. Thank you very much. I'll see you in another one.